Okay, we're still working with the matrix A equal 1, 2, 3, negative 4. Excuse me. And we want to find eigenvectors of V. An eigenvector, not eigenvectors of V, but eigenvectors V of the transformation defined by this matrix. So an eigenvector V has the characteristic that the transformed vector is parallel to the original vector. So as we've seen, we can have transformations that rotate everything, transformations that shear things, transformations that do all kinds of things to the unit square. Okay, we can deform the unit square. We're going to get a parallelogram out of the unit square, but it can have just about any shape. So we have some feeling for what a transformation can do. Now, if we want to transform so that some vectors, well, if there are vectors that transform to the same direction or to the exactly opposite direction, because a vector in the exactly opposite direction is a multiple of the original vector. So if we have such vectors, this actually can allow us to transform the transformation to different bases where the matrix is diagonal. Okay, that's a very desirable thing for many, many reasons that you'll become aware of. But we're moving toward the idea of diagonalizing a matrix. Eigenvectors have other important characteristics, other important applications. But diagonalizing a matrix is one of the big ones. Okay, so AV is parallel to V if AV is a multiple of V. Excuse me, I can't do anything about this, it's environmental. So, to say that AV is a multiple of V is to say that there's something we can multiply by V to get the matrix AV. And we're going to call that multiplier lambda. You've already seen this in chapter 3. Okay, you've already calculated eigenvectors, but you see a little bit more about why this is important and what it means geometrically right now. Okay, so anyhow, we have this, and this expresses the fact that the transformed vector is a multiple of the original vector. Okay, well, let's just let V equal xy, just in general. Call the components, the coordinates x and y. Okay, if AV equals lambda V, that means that A, this matrix, multiplied by xy, is equal to lambda times xy. Well, we can express the product of this matrix with xy as x plus 2y, x plus 2y, and then 3x minus 4y, 3x minus 4y. So that we have x plus 2y equals lambda x, 3x minus 4y equals lambda y. Oh, it gets much worse. I'm going to have to start over. And I know it's distracting. I do apologize. Okay. This gives us the two simultaneous equations. X plus 2y equals lambda x. 3x minus 4y equals lambda y. These equations are easily rearranged, just collecting terms on x. We're going to write this as x minus lambda x plus 2y, first equation. Second equation, we'll put the lambda y with the negative 4y. We're going to get 3x minus 4y minus lambda y, which then, if we factor out x, translates to 1 minus lambda times x, very clearly. And here, what do we have? We have negative 4 minus lambda times y. And I'm going to use a plus, negative 4 minus lambda, to indicate that. And I completely left y off there. Okay. Okay, so here are two equations, and these equations can translate back into a matrix equation. Well, 1 minus lambda, 2 in the first row, 3, negative 4 minus lambda in the second row. And you can verify that Multiplying this out gives you these equations. These equations give you this matrix equation. Now, this matrix equation is solvable for x and y, for non-trivial x and y, for x and y not equal to 0, only if this matrix isn't invertible. Because if this matrix is invertible, we could multiply the inverse by the 0, 0 vector, and what would we get? Well, any matrix multiplied by the 0, 0 vector is going to give you the 0 vector, okay? Which means that both x and y would have to be 0. We're trying to find x and y that aren't 0, that satisfy this. Because obviously, if x and y are 0, this is automatically satisfied, okay? A times a 0 vector equals lambda times a 0 vector, because both sides are going to equal the 0 vector. We're trying to find non-zero x and y that make this true. Again, this can only happen if this matrix is not invertible. And it happens if and only if this matrix is not invertible. Because the matrix is not invertible, we're going to be able to solve this. Okay, well, this happens. Matrix is not invertible, meaning the matrix is singular. A lot of different ways to say the same thing. That means that the determinant of the matrix would have to be 0. So in order to get a solution for x and y, the matrix has to have 0 determinant. Well, determinant of this matrix is easily written out and expanded. You get lambda squared plus 3 lambda minus 10. And that determinant has to equal 0. Well, that's just a simple quadratic equation. Now, we can do the same thing with 3 by 3 or 4 by 4, any n by n matrix. And if you have an n by n matrix, you're going to have a polynomial of degree n, not degree 2. So polynomial of degree n can't always be solved in any reasonable manner, but a quadratic always can. So we have this quadratic equation. We solve it using a quadratic formula. Right here's the solution, and I don't have to go over that with you. You understand how to solve a quadratic, and you can verify the solutions are -5 and 2. Although you could also solve this by factoring. You get lambda plus 5 times lambda minus 2 equals 0, and you would come to the same conclusion. Okay? Okay, well, now we have two values of lambda. Lambda is what we call the eigenvalue, so we have two eigenvalues. And eigenvalue means kind of like same value or corresponding value. What we're getting is eigenvectors, vectors that map onto multiples of the same vector, okay? So these are eigenvalues in any case. If lambda is -5, we can go back to these simultaneous equations here, and you can verify if lambda is -5, well, 1 minus -5 is 6. So we have 6x. And still have 2y. If lambda is -5, -4 minus -5 is -4 plus 5, that's 1. We have 3x plus y equals 0, there it is. And it's going to turn out, and it has to turn out, and you can think about why, if the determinant of this matrix is 0, these are going to be multiples of one another. Okay? The second row is a multiple of the first, basically, but the equations are multiples of one another. So any solution to the first equation is also a solution to the second equation. Okay, well, the first equation has solution y equals -3x if you just solve for y. Okay, so any y that's equal to -3x is going to solve this equation. And for the second equation, it's the same. You can rearrange the equation. You're going to get y equals -3x. Now, if y equals -3x, that means your vector, because remember, what we're talking about is vectors x, y, that means that this number is going to be -3 times this number. Okay? Well, one such vector is, we can write it this way, v1 would be x -3x, which is x times 1 -3. Okay? So the vector 1, -3 has this characteristic. Okay, you don't need the x, just plain old 1 negative, let x equal 1, then you get 1, -3. the vector 1, negative 3 multiplied by this matrix is going to give you negative 5 times the vector 1, negative 3. Okay, maybe I can find a space to write that out because that would be informative. Okay, so coming from over there, 1, 2, 3, negative 4 multiplied by 1, negative 3 gives us what? 1 and negative 6 is negative 5. 3 and 12 is 18. No, it isn't. 3 and 12 is 15. Multiplying 3 and 6 for some reason. You never know what's going to pop into my head. Okay, is this vector negative 5 times this vector? Darn right it is. Negative 5 times 1 is negative 5. Negative 5 times negative 3 is 15. So that proves that this is an eigenvector with eigenvalue negative 5. Okay, if lambda is 2 with the second eigenvalue, we can do the same thing, and our solution, well, our equations become negative x plus 2y equals 0, 3x plus negative 6y equals 0. This equation is negative 3 times this equation. Negative 3 times negative x is 3x. Negative 3 times 2y is negative 6y. So any solution to one equation is a solution to the other, and if we solve for y, we get y equals 1/2 x. So that our vector v2, we'll call it v2, our second eigenvector, is lambda 2 standing for the eigenvalue here, times x, 1/2 x. And that's, of course, gives us a vector v2. One vector is just x times 1, 1/2. And in fact, 1, 1/2 is a sufficient eigenvector. And we can verify that 1, 2, 3, negative 4 multiplied by 1, 1/2 gives us a vector that's, well, it multiplies this vector by 2. We get 2, 1. Let's verify that. 1 times 1 is 1, 2 times 1/2 is 1, 1 and 1 is 2. 3 times 1 is 3, negative 4 times 1/2 is negative 2, 3 minus 2 is 1. This vector, 2 times 1 is 2, 2 times 1/2 is 1. So here's another vector. Now it's going to turn out, just as a preview, that if we let a new basis B be the basis of these eigenvectors, it doesn't have to be negative 5, 15. That's, sometimes I'll write down what I see. Negative 5, 15 would not be an invalid vector to use. Any multiple of 1, negative 3 would work, but let's use 1, negative 3 because the numbers are about as small as they can be without being fractional. And we have 1, 1/2, and actually I'm going to use 2, 1. We can use any vector that satisfies this condition where y is 1/2 of x, so I'm going to choose 2, 1. According to this basis, I'm going to give you a preview. We'll see why this works soon enough. But according to this basis, the matrix is represented by this transformation. Diagonal matrix with the first eigenvalue, the eigenvalue corresponding to this first vector being negative 5, eigenvalue for the second vector being 2. This matrix will multiply this vector by negative 5, multiply this vector by 2, and give you the basis for your whole transformation. Now, you don't need to remember that now, but remember that in the preceding video, or maybe video before last, we talked about expressing a transformation by a matrix according to the standard basis or according to another basis, and we talked about how the matrices for that transformation relative to the two different bases are related. Okay, so when we do this, we're going to have an especially simple matrix in the space whose basis is your vectors. Again, eigenvalues are going to appear in the diagonal, and it's going to be really quite useful. So that's where we're going. We're not there yet, but you'll see where we end up.